Get ready. Imagine this. A cosmic ghost, a visitor not from our neighborhood, crosses the backyard of our solar system. It makes no noise. It doesn't generate big headlines at first, but in the quietest corners of NASA centers and telescope networks, its arrival triggers what some call the biggest silent alert since 1997. And I, with access to that data and the analysis from the teams who know how to listen best, will tell you exactly why. This is not a fictional documentary. It is the real story of 3I Atlas. From the very first second, I propose a clear mental image. A visitor that does not belong to our cosmic neighborhood crosses the backyard of the solar system. It makes no noise. It leaves no strident headlines. But it quietly awakens the teams who know how to listen best. That visitor is called 3I Atlas, and it is the third confirmed interstellar object we have observed from Earth. For some corners of the internet, its arrival is NASA's biggest silent alert since 1997. For the scientific community, it is, above all, a rare opportunity and a challenge of precision. In this episode, we will separate the inflated narrative from the verifiable facts. Before we continue, I would love it if you write in the comments where you are watching this video from. It's always very special to know how far our stories reach. And if you are enjoying the content, consider giving it a like and subscribing to the channel. That helps me know if I'm on the right track and if you want to see more videos like this. Let's start with the solid facts. 3I Atlas was discovered in 2025 by the ATLAS System, Asteroid Terrestrial Impact Last Alert System, a network of telescopes in Hawaii dedicated to searching for near-Earth objects. The I in its name is not for decoration. It means interstellar. Like 1I Oumuamua in 2017 and 2I Borisov in 2019, it was not born here. It comes from another star system, and its orbit is hyperbolic, meaning it will enter and leave, never to return. So far, as they track its trajectory, no impact risk has been reported. This is key. High scientific interest does not equal danger. Why then so much attention? Because an interstellar object offers unique clues about how worlds form and evolve far from our Sun. Furthermore, measuring its position, brightness, and subtle accelerations, for example, those caused by jets of gas erupting as it heats up, is a major technical challenge. Hence, international networks like the Minor Planet Center, which coordinates observations, and the International Asteroid Warning Network exist, not to create panic, but to standardize methods, share data, and improve orbits as quickly and accurately as possible. There's another point worth clarifying from the start. In astronomy, a coordinated campaign does not mean a red alert. It means aligned schedules, common protocols, and a shared technical language so that telescopes on different continents see the same thing in a comparable way. If it sounds uncinematic, it's because serious science is often like that. Rigorous, patient, not fond of haste. And yet, 3I Atlas touches a sensitive nerve. The memory of Oumuamua, whose non-gravitational accelerations triggered intense and legitimate debates, and the classic Cometary trail of 2I Borisov, which seemed more familiar. With 3I, the sample size goes from 2 to 3, and every new piece of data can shift what we believe we know about interstellar visitors. The question then is not whether to worry, but what we can learn by observing it with all available precision resources. And what would that reveal about our real capacity for planetary defense when the sky poses difficult questions? To understand why 3I Atlas arouses so much interest without falling into alarmism, one must look at how an interstellar visitor is detected and validated. The route does not start with headlines, but with raw images captured by systems like Pan-STARRS, CTF, Catalina, and Atlas itself. Repeated shots of the same star field, separated by minutes. Software subtracts one image from another and looks for points moving against the fixed background of stars. When something moves with the right speed and direction, a detection is generated. Several well-linked detections form a tracklet, a short track of movement. This material goes to the Minor Planet Center, MPC, which acts as a single window. There, observations from different telescopes are aggregated and a preliminary orbit is calculated. If the first adjustments show an eccentricity greater than 1 and an excess velocity compatible with an object not bound to the Sun, the bell rings. We might be looking at an interstellar object. But might is the key word. Young orbits are fragile. With few measurements, the margin of error is huge. That's why the next step is to coordinate high-precision astrometry. More telescopes, consistent filters, accurately timed observations, and reference catalogs like Gaia to anchor positions rigorously. Before continuing, I would love it if you leave in the comments what topics you would like to see here on the channel. It's always very special to bring content that you are really interested in. And if you are enjoying the video, don't forget to give it a like and subscribe to the channel. That lets me know I'm on the right track and that you want to see more videos like this. This is where some people hear coordinated campaign and mistakenly translate it as red alert. In reality, what exists is method, agreeing on aperture sizes, exposure times, photometric filters, and data reduction protocols. The goal is to reduce the angular uncertainty, sometimes to tenths of an arcsecond, so the orbital fit stops shifting with each well-measured night. The hypothetical ellipse is refined until it reveals its true nature. Hyperbola if it's a visitor, ellipse if it's a resident. Besides position, brightness and its change with distance from the Sun are measured. In comets, that brightness is contaminated by the coma, gas and dust, which can deceive algorithms about the object's true center. That's why deconvolution techniques and multiple photometric apertures are used. One for the coma, another more compact one pointing to the nucleus. Centroids are compared and biases are evaluated. All this sounds technical, and it is, but without that detail, a big conclusion can rest on a small error. And why is it so important to reduce that error? Because at the limit of precision lies the question that changed recent debates. Does what we see obey only gravity? Or are there non-gravitational accelerations, gas jets, fragmentation, pushing the object? If that push exists, it is tiny. If we mistake it for noise, we invent ghosts. If we measure it well, we open a new window to the physics of interstellar visitors. And to something more uncomfortable. How ready are we to detect them in time when it does matter? If we sharpen the focus from how we measure to what we seek, 3i Atlas becomes an ideal laboratory to test 3 blocks of serious questions. First, its composition. What it reflects and emits tells us about ices, dust, and molecules that may not be abundant in local comets. Spectra, that fingerprint of decomposed light, allow us to identify gases like CN, C2, CO2, and estimate how volatile its surface is. In interstellar objects, these ratios could deviate from the typical, not for gratuitous exoticism, but because they formed under other stars, with different temperatures and chemistries. A chemical pattern different from ours is, in itself, a window into another stellar nursery. Second, its structure. The brightness doesn't always come from a single nucleus. Sometimes there are clumps in the coma or microfragments that distort the centroid. Separating these contributions requires comparable photometric apertures between telescopes and careful algorithms to avoid confusing noise with signal. If the brightness comes from an asymmetric halo, it tells us something about the nucleus's outgassing. If it comes from 2 very close points, it tells us the structure might be subtly fragmenting. Third, its fine dynamics. Small deviations from a purely gravitational orbit betray jets, spins, or mass loss. For 3i Atlas, the goal is not to declare a mystery by decree, but to measure whether any non-gravitational acceleration exists and what its size is. That parameter, described in catalogs with tiny coefficients, is fed by weeks of consistent astrometry. If it appears, it is modeled. Jet direction, nucleus rotation period, evolution with solar distance. If it doesn't appear, that's also news. The object behaves as expected. And that helps put 1i Oumuamua and 2i Borisov in context, narrowing down how varied interstellar visitors are. Planetary Defense enters here soberly, not as a siren, but as a discipline that learns from real cases to improve reaction times, protocols, reference catalogs, reporting formats, and reduction pipelines. They are not glamorous, but they shorten critical hours when it comes to closing uncertainties. Confusing a methodical campaign with an impact alarm is a mistake. What is pursued is strengthening the chain: detection, confirmation, characterization, prediction. A less flashy but crucial aspect is the observing geometry. Earth's rotation and the object's position relative to the Sun dictate short windows, sometimes minutes, when the signal is usable. Linking Hawaii with northern Chile or the southern hemisphere allows passing the baton and maintaining continuity. Real conditions. This competes with clouds, bright moonlight, and, lately, satellite trails crossing the field. That's why priority lists are designed. What to measure if the sky holds out for little time. What to sacrifice without losing key physics. All this leads to a question that goes beyond 3i Atlas. If tomorrow another visitor arrives, fainter, faster, or with less cooperative behavior, do we already have the technical muscle not to lose it? Or are we missing pieces in the chain that we still don't want to see? Looking at 3i Atlas without the noise of myth requires learning from the two previous cases. 1i, Oumuamua, left us with an uncomfortable lesson. When you don't have enough data, imagination runs faster than statistics. It arrived, was recognized late, faded quickly, and the set of scarce, heterogeneous measurements with unfavorable geometry opened doors to hypotheses ranging from supervolatile ices to solar radiation pushing a body with unusual proportions. Sober conclusion. Uncertainty dominates when the observational window is short and methods are not fine-tuned for the type of object. Borisov, on the other hand, offered the textbook Cometary case. Evident coma, spectra with familiar molecules, dynamics compatible with jets. It was the case that demonstrated an interstellar visitor can behave like a local one, and that with early warning, the community obtains quality spectra, light curves, and astrometry. With that background, 3i Atlas faces more realistic expectations and better oiled procedures. First, prioritize homogeneity, using common reference catalogs, Gaia, carefully time-stamped observations, and comparable photometric apertures prevents an instrumental bias from disguising itself as exotic physics. Second, close the cadence. Covering consecutive nights, coordinating longitudes, and confirming dubious measurements reduces the temptation to force interpretations. Third, separate brightness from position. The coma deceives. Calculating centroids with and without its contributions helps avoid confusing the direction of a jet with a mysterious acceleration. The way of communicating has also changed. Serious science learned that the public understands phrases like "we don't know yet" if they come with what needs to be measured and when there will be clarity. Modern planetary defense operates in that framework. Protocols, shared dashboards, performance metrics, for example, how much the uncertainty ellipse shrinks after each night. No sirens, yes indicators. An additional challenge is managing priors. With a sample of just 3 visitors, any strong conclusion risks being overfitted. The antidote is comparability, reporting the same physical parameters between cases, non-gravitational coefficients, gas production rates relative to solar distance, color evolution, to build a base that allows talking about diversity, not miracles. And there is a crucial tactical point: timing. Near perihelion, comets change quickly. Far away, they are elusive. Knowing when the object will be bright enough but still stable for fine measurements defines whether the campaign yields solid science or collects noise. That short, demanding time frame with no second chances is where 3i Atlas can decide if it resembles 2i Borisov, 1i Oumuamua, or inaugurates a third behavior we don't yet know how to name. For 3i Atlas to yield solid science, pointing telescopes is not enough. We must tame the error. In astrometry, minimal deviations are cooked in details that rarely make headlines. Let's start with the reference frame. Today, almost all precision astrometry is tied to the Gaia catalog, which offers positions and proper motions of billions of stars. Using it well involves correcting for parallax, annual aberration, atmospheric refraction, and even subtle variations in the reference star's color relative to the chosen filter. Each correction reduces milliarc seconds that, projected to astronomical distances, become hundreds of kilometers in the estimated trajectory. Then there is the instrumentation. Two identical cameras do not exist. Each CCD has pixels with slightly different responses, noisier columns, hot pixels. Teams take bias, darks, and flats daily to characterize these imperfections and build a correction map. Comets. Additionally, the PSF, the blur of a point-like star, is not the same animal as the diffuse coma. That's why mixed models are adjusted. Measurements are taken with increasing apertures, deconvolved, and the centroid is compared with coma and coma removed. If both coincide within the uncertainty, the position is reliable. If not, biases must be reviewed or real physics considered, like asymmetric jets. The real sky also fights back. The ionosphere changes refraction with time and solar activity. A front of high clouds adds dispersion, and the growing mesh of satellite trails introduces saturated lines that bias centroids if not masked. That's why, in serious campaigns, each image is accompanied by quality masks and a minimum SNR indicator per measurement. Detections below the threshold are archived, not forced. Better, one less point than a false positive that contaminates the entire orbit. What about other techniques? Planetary radar is gold for nearby asteroids, but for a distant interstellar visitor, unfeasible. The signal falls with the fourth power of distance. In the infrared, observatories like JWST or ground-based cryogenic instruments can isolate warm dust and CO2 emission lines, useful for distinguishing reflected solar energy from thermal emission. That separation allows estimating effective sizes and gas production rates with less ambiguity than in pure optical. Everything leads to rigorous logistics, observation queues with dynamic priorities, rules for repeating dubious measurements, and coordinated windows between hemispheres. The goal is not the aesthetics of a spectacular image, but homogeneously filling the timeline that feeds the orbital adjustments. Because the next step, the one that decides if 3i Atlas confirms the expected or pushes the limits, does not depend on one bright night, but on a robust series capable of sustaining a conclusion without adjectives. And that series is about to reveal whether the push some into it is noise or signal. If all this effort to tame the error is worthwhile, we must look at the institutional framework that activates without sirens when an unusual object appears in the sky. Modern planetary defense is not a single office with a red button. It is a coordination chain with clear links. The Minor Planet Center has a node for collecting and distributing observations. NASA's Planetary Defense Coordination Office, PDCO, has a coordinator of efforts in the U.S. The International Asteroid Warning Network, IAWN, to standardize alerts and observations, and the SMPAG, Space Missions Planning Advisory Group, which coldly discusses mitigation options internationally. That architecture exists so that technical matters do not depend on drama, but on protocols. The learning didn't come from nowhere. In 1997, asteroid XF11 generated media stir when a preliminary calculation suggested a worrisome close approach in 2028. More data erased the alarm, but left a lesson. Communicating uncertainty requires method and timing. From there, tools like the Torino scale to communicate risk understandably, the Palermo scale to evaluate technical significance, and continuous monitoring systems like Sentry were consolidated. The motto: publish live risk tables with transparent criteria and adjust in real time as new data arrives. The goal is not to generate headlines, but to avoid misunderstandings. Where does 3i Atlas fit into that ecosystem? In the box of high scientific value object which, being interstellar, deserves fine astrometry and photometry, and a coordinated observation plan. That does not turn it into a risk by itself, but makes it an ideal test bed for the gears of coordination, homogeneous formats, rapid data exchange, quality criteria, and key, sober communication. If something were to move from the side of uncertainty to concern, the channels are already traced. First, the orbit is closed with additional observations. Then it is evaluated with accepted scales. Finally, context and numbers are communicated, not adjectives. It is also important to understand when to speak and what to say. A premature statement can freeze resources where they are not needed. A late one erodes trust. That's why Planetary Defense prefers continuous technical bulletins and, if required, clear conferences that explain what changed and why. In that spirit, 3i Atlas helps rehearse the orchestra. How quickly does useful information flow? How well do the observatories agree? How robust is the timeline feeding the models? Because what is at stake is not just describing a rare visitor, but proving that when the odds are ever against us, the links are already tempered. And while the numbers for 3i Atlas accumulate in silence, a graph begins to draw a trend that will force a decision on whether we are seeing just instrumental noise or the consistent trace of a real acceleration. If the institutional machinery maintains order, the sky imposes its own rules. The fine observation of 3i Atlas occurs in a changing environment: atmosphere, ionosphere, and space weather. Geomagnetic storms alter light propagation and affect clocks and positioning systems that observatories use to timestamp with millisecond precision. In photometry and astrometry, a time mismatch or a poorly corrected refraction can displace the centroid enough to resemble exotic physics. The professional response is prosaic and powerful: redundant calibrations and quality filters. Each image is accompanied by indicators of seeing, transparency, signal-to-noise ratio, and condition notes. If a threshold is not met, the measurement does not enter the orbital fit. There are no lone heroes. There are criteria. At the ground level, teams operate with dynamic lists. If the moon is high, they prioritize spectra less sensitive to bright background over extreme astrometry. If a band of cirrus clouds increases dispersion, exposures are shortened and the number of shots is increased to average noise. The idea is simple: don't leave gaps in the chronology that feeds the models. In parallel, the community has advanced in algorithms that better separate coma from nucleus, modeling the brightness shape with functions that combine the footprint of a point star, PSF, and a diffuse halo. This allows comparing position with coma versus coma-removed position and detecting biases quantitatively, not by eye. There is also a layer of prudent automation. Machine learning tools are applied to well-defined tasks, classifying images contaminated by satellite trails, improving centering on faint objects, or suggesting the next window that most reduces the orbital uncertainty given Earth's rotation and local forecast. They do not replace human judgment. They summarize information so astronomers can dedicate time to deciding where a valuable hour of sky is best spent. An often ignored point is photometric coherence between sites. Changing from an R to an I filter or from a 3 to a 5 aperture without documenting it introduces discrepancies that are confused with the object's intrinsic variations. That's why standardized reports require specifying filter, aperture size, local sky method, and catalog used. In an interstellar visitor, where we seek subtle variations with solar distance, that discipline marks the difference between seeing a real pattern and chasing an instrumental mirage. With these safeguards, 3i Atlas stops being a rumor and becomes a time series. Positions with traceable error bars, comparable brightness, spectra repeating lines. And it is precisely when the series becomes reliable that it's worth asking what truly matters. If, after discounting atmosphere, instruments, and statistics, a residual push remains that gravity alone cannot explain, how big is it? In what direction does it act? And what does it tell us about the nucleus itself? Because the next technical decision will depend on those three figures. With the time series in hand, the next step is to model what gravity does not explain. In comets, a family of models has been used for decades that introduces tiny non-gravitational terms in three directions: radial, A1, towards away from the Sun; transverse, A2, along the orbit; and normal, A3, out of the orbital plane. They are not magic. They represent the thrust from gas jets acting like an irregular rocket. If you fit an orbit with gravity alone and the residuals, observed, calculated, show coherence, you try a solution with A1, A3. If the fit improves and the parameters remain stable when adding new nights, it's not a whim of the model, it's a signal. But there is fine print. Those terms depend on how much activity the nucleus has and how it changes with solar distance. An activity law that increases near perihelion is usually used, because more heat is attributed to more sublimation. The subtlety is that jets don't turn on and off ideally. The thermal lag, ices absorb heat and respond with hours of delay, and the comet's rotation, which exposes and hides active regions, mean the effective thrust does not point exactly towards the Sun, nor is it constant. That's why, besides A1, A3, it helps to measure light curves to infer a rotation period. If the brightness modulates periodically, perhaps the thrust direction does too. In parallel, photometry provides a practical indicator, AFR, A rho F, which summarizes the amount of dust near the nucleus relatively independently of telescope size if used correctly. If AFR and spectral lines of gases, CO, CO2, CN, increase, you would expect positive A1 anti-solar thrust growing near perihelion. If instead the fit calls for notable A2, you might be seeing asymmetries aligned with the direction of motion. A persistent jet at a specific latitude or even a spin change from outgassing torque. The A3 component, out of plane, is rarer and more revealing when it appears. Little instrumental physics can fake it. It usually points to jet geometries tilted relative to the orbital plane or to incipient fragmentation that displaces the center of mass. Fragmentation, by the way, leaves traces: widening of the coma, subtle multiple tails, and sometimes centroid duplicity if pieces start to separate. That's where it's useful to compare position with coma versus coma removed, as we did, and seek consistency across several telescopes. The common thread is coherence. Parameters that don't dance from night to night, light curves that repeat phase, spectra confirming activity compatible with the deduced thrust. If everything fits, 3i Atlas is not a capricious enigma, but a case study that calibrates how much and how interstellar visitors push. And if something doesn't fit, a stubbornly different A3, a jumping period, an AFR that rises without apparent thrust, then we must open another fine door, that of processed species that may hide the true engine. If the non-gravitational terms tell us how 3i Atlas moves, the composition tells us why. The key is to look beyond the visible. In optical, we measure brightness and color. In near and mid-infrared, bands of H2O, CO2, and CO appear, revealing which fuel the nucleus responds to when heated. In ultraviolet, transitions of CN and other species trace the photochemistry in the coma. Each one weighs in the balance of thrust. A TO and CO2 sublime at lower temperatures than water and can activate jets earlier than intuition dictates, generating a pull when the object is still far from the Sun. If the spectrum favors those molecules, it shouldn't be surprising that A1 grows early. It's not just what gas is there, but how much dust accompanies it. The dust-gas ratio conditions the opacity of the coma, and the way solar radiation pushes the system. Here, polarimetry and phase photometry come in, how scattered light changes with the Sun-Comet-Earth angle. More porous or finer grains produce distinct signatures, and that feeds back into radiation and drag models. With 3i Atlas, coming from another stellar nursery, it wouldn't be strange to find uncommon mixtures for us, but scientifically plausible, more CO relative to H2O, for example, or grains with coatings that alter their reflectance. Thermo-infrared adds another piece. It separates brightness from dust heat from brightness by reflection. If the dust glows thermally more than expected for its distance, perhaps the grains are dark, low albedo, and absorb sunlight better. If not, they could be brighter and therefore more susceptible to radiation pressure. In parallel, emission lines allow estimating production rates, how many molecules per second leave the nucleus. With those figures, thrust models stop being abstract. One can ask if the amount of gas is enough to explain a measured A1 or A2, or if geometry is needed, concentrated jets instead of global hyperactivity. There is a subtle factor: the comet's skin. Over millions of years in the interstellar medium, cosmic radiation can generate a hardened chemical crust that delays or channels sublimation. Upon entering the solar system, that crust does not melt uniformly. It cracks, patches, and opens natural valves. That would explain why the thrust isn't perfectly aligned with the sun and why activity increases in fits and starts. Laboratories on Earth simulate part of that processing with irradiated ices. The results show organic compounds that change the surface tension and porosity of the material, precisely what determines whether a jet is smooth or like a shower spray. Thus, spectroscopy, polarimetry, and infrared not only paint a chemical portrait, they impose hard limits on any dynamic interpretation. If the molecular inventory isn't enough to push what is observed, the dilemma stops being philosophical and becomes physical. Either we are measuring wrong, or there is an additional mechanism at play. Which one? The answer could lie in how charged dust and the solar wind interact with a nucleus that brings an electrical history from another neighborhood. If chemistry suggests the fuel, electromagnetic interactions explain part of how it is shot out. Comets don't travel in an ideal vacuum. They move within the solar wind, a flow of plasma that drags the interplanetary magnetic field, IMF. The dust and gas escaping the nucleus can ionize under ultraviolet radiation and, upon charging, stop obeying only gravity. That's when the ion tail appears, thin, bluish in wide-field images, pointing almost anti-sunward, shaped by field lines. Although 3I Atlas is faint, if its activity is enough to produce detectable ions, it becomes a seismograph of the local space environment. How to test this without inventing physics? With correlations. Teams can cross the small astrometric deviations, after subtracting coma and instrumental errors, with solar wind parameters measured by probes like ACE, DSCOVR, or Solar Orbiter. Flow speed, density, IMF orientation. If the residuals change synchronously with field rotations or increases in dynamic pressure, for example during interplanetary shocks, we would be seeing signal, not noise. In parallel, polarimetry can detect changes in dust size and charge. Variations in the degree of polarization with the phase angle can indicate that grains are being selected by electromagnetic drag, not just by radiation. An additional test is morphological. Deep images separate the dust tail, wider, curved by radiation pressure, from the ion tail, straight, sensitive to the IMF. If the ion column flickers or bends to the rhythm of space weather, geomagnetic storms, solar rotation bringing different field sectors, the hypothesis gains strength. All this can be quantified with simple magneto-hydrodynamic models fed by public solar wind data, without heroic assumptions. There is, however, a healthy limit. Electromagnetic forces on the nucleus itself are tiny compared to gravity. Where they can move the needle is in the ejected material that defines the coma and, therefore, biases the centroids if not corrected. That's why the key is in the double finish. Coma-removed astrometry for the nucleus and photometry and imaging for the coma. If both worlds tell the same story, reactive ion tail and stable centroids after correction, then the dominant thrust remains classic outgassing. If instead even the clean position leaves a residual that grows during solar wind events, the model must be refined, perhaps pockets of concentrated activity, perhaps a rotation period that aligns jets with the field in non-obvious ways. And right here, timing comes in. As solar conditions change in the coming weeks, 3i Atlas could gift us a natural experiment. If the signature repeats with each solar wind pulse, we will have a clue. If not, we must look inward at the nucleus itself, its spin, its torques, and the way heat is reconfiguring it from skin to core. If the solar environment can modulate the coma, 3i Atlas's internal clock decides its choreography. The nucleus's rotation governs where and when jets turn on, and that pattern, more than any external gust, sets the average direction of non-gravitational thrust. How do you measure the spin of something we can't see directly? With light curves, brightness series taken at constant cadence that reveal a periodic modulation as surfaces with different reflectance and activity rotate in and out of sunlight. In a faint comet, the signal is subtle. That's why small apertures are used to prioritize the nucleus, and the local sky is corrected with surgical care. When a reliable periodicity appears, the next step is to verify it's not an alias, a false period created by the sampling window. The cadence is rotated, compared between sites, and tested with Lomskargel analysis and time domain fitting. A stable period opens the door to a bigger question. Is the nucleus spinning like a simple top? Or is it in precession, tumbling, complex rotation? The second case complicates everything. The instantaneous direction of the jets changes with two frequencies, and the effective thrust can dance even if the average activity doesn't rise. To detect it, harmonics in the light curve and phase changes that don't fit a single period are sought. High signal-to-noise images sometimes show veils or fans in the coma that rotate night by night. If those fans follow a double pattern, tumbling gains points. Spin is not just diagnostic, it's also dynamic. Jets feed back into the system via outgassing torques that can accelerate or slow the rotation. This effect, observed in solar system comets, can change the period by fractions of an hour over weeks near perihelion. That's why well-designed campaigns repeat photometry with the same configuration and compare dP, change in period, against gas production. If the period shortens quickly, the shear stress inside the nucleus increases. If it lengthens, perhaps activity migrates to latitudes applying an opposite torque. In both cases, internal mechanics, porosity, cracks, layers annealed by radiation, come into play. A significant dP brings a known risk: structural stability. Small, fragile nuclei can cross thresholds where rotation facilitates breaks or local detachments. Early signs are not dramatic. An asymmetric widening of the coma, a faint secondary tail, small discrepancies between centroids with and without coma that persist even after quality checks. That's why astrometry and photometry must walk together. One measures the thrust, the other indicates the stress. If both point in the same direction and the period starts to slip night after night, the script is no longer dictated by the solar wind, but by the internal physics of a visitor that might be reconfiguring itself in real time. And when a nucleus's architecture gives way, the next footprint is usually not subtle. If the period starts to slip and photometry suggests stress, the next natural chapter is fragmentation, not as a fireworks show, but as a process that often begins silently. The first thing to change are the shapes. In deep images, healthy comets show an approximately symmetric coma and a dust tail whose axis follows predictable rules with the Sun-Comet-Earth angle. When the nucleus cracks or a chunk detaches, the field gets complicated. Fans appear that don't rotate with the expected phase. Isophotes, lines of equal brightness, stretch more on one side, and secondary tails so faint they only show when stacking tens or hundreds of shots. To hunt that signal, teams use two complementary strategies. The first is deep imaging with large aperture telescopes and dark skies, longer exposures, masks to eliminate satellite trails, and careful sky subtraction techniques to not eat real signals. The second is high-cadence differential astrometry, measuring positions with small apertures that clip the coma and tracking micro-displacements of the centroid throughout the night. If the centroid jitters with the preferred direction and that preference coincides with a fan in deep images, the fragmentation hypothesis gains weight. Another clue is color. Freshly exposed dust can reflect light differently from the mature material in the coma. That's why sequences in multiple filters, for example R and I, are obtained and a color index is built along the tail. A sharp gradient aligned with a new morphological feature suggests recent injections of material. In spectra, a sudden increase in lines like CN or CO2 without a proportional increase in dust reflectance could indicate cracks venting gas without lifting much grain, at least initially. The most delicate part is separating instrumental ghosts from real changes. A bad flat can create wings. Poor masking of background stars mimics clumps. That's why, in possible fragmentation, independent confirmation is requested. Another observatory, another night, another camera rotation angle. If the feature persists with different configurations, it stops being suspicious and becomes data. And what does detecting a fragment mean in science? Geometry and mass. A small piece near the nucleus can travel almost parallel for days or weeks, subtly altering the integrated photometry and centroids. As it separates, it could become resolvable as a secondary nucleus of very low surface brightness. That's where telescopes with excellent seeing and point spread function fitting techniques come in to distinguish if there are 2 points of light hidden in the same blur. The uncomfortable question is not, did it break? But how and when did it break? Because on that, how depend the next decisions? What photometric cadence is best? What filters to prioritize? And if it's worth betting on a night of ultra depth that might reveal more than a fan, perhaps the trace of a tiny companion that, if confirmed, would rewrite the dynamic map of 3I Atlas in a matter of days. If possible, fragmentation is the what. The when and how much are answered by the dust. A comet's tail is not an ornament, it's a forensic record of the ejection calendar. To read it, teams use the classic Finson-Probstein model, which separates the tail geometry into synchrones, lines of particles launched at the same instant, and syndynes, lines of particles with the same V, the ratio between radiation pressure and gravity. In plain language, a map where each trace tells you how big the grain is and when it left the nucleus. With deep images and good scale, you can reconstruct discrete outbursts or continuous activity without needing to guess mechanisms. The workflow is methodical. First, the image is cleaned, background stars masked, sky gradient corrected, and signal-to-noise improved with stacking aligned to the comet's motion. Then, synchrones are traced for candidate dates. For example, 1 week, 3 days, 24 hours before, and syndynes for typical V values, from millimeter grains with small v to microns with large V. When a real fan sticks to a family of curves, you get 2 things: emission date and size range. If the pattern points to a brief interval, we speak of a burst. If it's a fatter fan following many synchrones, it's sustained activity. With that clock in hand, photometry delivers the final blow. The AFR parameter gives a measure of the dust content in an aperture. Combined with the synchrone syndyne map, you can infer a velocity law, small grains leave faster, and a size distribution, a power NA, K. If K is high, fine dust dominates and the tail becomes long and thin. If it's low, there are more large grains and the tail looks heavier. This matters for astrometric bias, which grains dominate near the nucleus. Large, slow particles, less pushed by radiation, weigh more in the centroid than a cloud of microns moving away quickly. The temporal film also distinguishes fragmentation from a stationary jet. A stable jet modulated by rotation leaves a fan structure that changes smoothly with the phase angle. A sudden break generates narrow synchrones that emerge uniquely and freeze in the tail like tree rings. If that temporal signature also coincides with a jump in the light curve or a measurable dP in the rotation period, the case becomes strong. Something physical happened in the nucleus, not in the intermediate sky. There is one finer crossover, comparing the burst date with the expected thermal evolution of the nucleus, subsolar latitude, thermal skin depth, inertia, and with the solar environment, solar wind pulses, field changes. If the dust clock points to an exact instant, was it triggered by accumulated heat, a torque that pushed the material to the limit, or a chemical window that opened suddenly? The answer dictates where to look with everything: infrared for gas, polarimetry for dust, or thermal models that might reveal a tension that had been building for some time. If the dust clock marks a date, the next step is to ask what internal physics could have pulled the trigger just then. A comet nucleus is a mosaic of ices, dust, and voids with high porosity. Its response to the sun is not uniform. The surface absorbs energy. Part is re-radiated as heat, and part is spent sublimating ices, H2O, CO2, CO. The local energy balance can be expressed essentially as incoming radiation, outgoing radiation, plus conduction, plus sublimation. From that equality come two numbers that govern almost everything: the thermal inertia, how quickly the temperature changes, and the skin depth, how deep the heat penetrates in a day-night cycle. If the thermal skin is 100 centimeters, the heat stays stuck to the crust. If it's larger, subsurface layers start to participate and can feed jets delayed relative to local noon. That thermal lag matters because it synchronizes or desynchronizes activity with rotation. In regions with ice buried under a more refractory crust, gas seeks fractures to escape. When the pressure exceeds the material's cohesion, on the order of pascal to tens of pascals in fragile nuclei, the crust yields. No explosion is needed, just the detachment of plates, a spring that opens and closes on a macroscopic scale. That valve creates a directional jet. Structurally, it introduces stresses that, added to the outgassing torque, can modify the rotation period, dP, and lead the nucleus to zones of centrifugal instability. Here, mechanics come in. A porous body with low tensile strength can tolerate moderate spins, but if dP pushes towards short periods, the tangential stress grows and pre-existing cracks activate. The threshold is not universal. It depends on shape, lobes, narrow necks, void distribution, and ice humidity. Laboratory tests with porous analogs show that small variations in humidity and compaction change the resistance by orders of magnitude. Translated: a nucleus that was stable yesterday can cross an invisible limit today because a jet migrated half a degree in latitude. Simplified thermal models, semi-infinite slab, fixed rotation, homogeneous properties, are enough to estimate if an insolation peak could have triggered the burst red in synchrones. But crude cases fall short when there are topographic shadows, self-heating, walls facing each other, and material heterogeneity. That's why, when the clock points to a tight instant, it's worth feeding 3D models with shapes derived from photometry, inversion techniques, or, at a minimum, exploring families of solutions that include active patches at different latitudes. If only a latitude band simultaneously reproduces the burst date, dP, and the direction of A1, A3, the portrait sharpens. Not only did the comet activate, but it opened here, at this hour, and with this torque. One loose and powerful end remains. What if the energy is sufficient, but the observed pattern suggests more valving than an open jet? In that case, the temporal signature should repeat with the cometary day as a metronome, unless something is changing the metronome itself, and when the clock becomes mobile, the next clue stops coming from the sun and appears in the geometry of the spin. When the internal metronome changes, the spin geometry stops being a detail and becomes the key to everything. A nucleus can rotate in a stable principal axis, like a well-centered top, or in non-principal axis rotation, tumbling, where it precesses and nutates at the same time. This difference is crucial because the instantaneous orientation of the jets defines where the comet pushes at each moment, and the temporal sum of those pushes is what we measure as A1, A3. If the axis dances, the effective thrust can appear capricious when it's pure geometry. How is that dance dissected? First, with long, well-sampled light curves to look for multiple periods, one of rotation, another of precession. The analysis doesn't stop at Lomskargel. Composite models are explored, and the stability of the solutions is verified by removing changing apertures and mixing observatories. Second, with coma morphology, rotating fans and veils can act as clock hands. If the pattern repeats with two frequencies, tumbling gains points. Third, with jet modeling. A small number of active regions on the surface is assumed, and the latitude, longitude of those patches, their angular aperture, and relative strength are adjusted to simultaneously reproduce the light curve and the direction of non-gravitational thrust. There are common traps. Phase geometry, Sun-Comet-Earth angle, can mimic periodic variations if the brightness dependence on phase is not corrected. Also, series taken only from one terrestrial hemisphere can induce irresistible aliases. Nice periods that disappear as soon as data from another longitude is added. That's why the finest campaigns force longitude coverage and cross-filters to ensure the period isn't an artifact of color or coma. Once the spin state is proposed, pole solutions come next, where the rotation axis points in ecliptic coordinates and how it moves over time due to outgassing torques. Solving this is not academic. If the axis precesses, the seasonal insulation of each active patch changes, and with it, the thrust power. This directly impacts the orbital prediction. An A1, A2 that seems small today could grow or reverse if the orientation favors another patch. The line between noise and signal becomes scheduled. The elegant closure is statistical, testing model families with Monte Carlo, propagating how each spin solution would affect the A1, A3 terms in the coming weeks, and seeing which ones survive the clash with new nights of data. If a narrow subset explains positions, brightness, and morphology, then we not only understood the dance, we can predict when it will push more and in which direction. And that capacity, anticipating thrust, is what separates a nice case from an instrument for fine-tuning forecasts. Because if the axis announces a regime change that will move the orbit perceptibly, the next question is not whether we will see it, but whether we will be ready to correct the trajectory in the models in time before the critical window closes. If we already understand the nucleus's dance and the thrust it can exert, it's time to see how that translates into predictions. In small-body astronomy, the art of saying where something will be rests on something less glamorous than any image, the covariance matrix. Each position measurement comes with errors. When fitting an orbit, those errors propagate and generate an uncertainty ellipse in the sky, and, by extension, a fan of possible trajectories in 3D. There is no single true orbit, but a family of equally plausible solutions within the error margins. The key is to reduce that family with quality observations separated in time and, if possible, taken from different geometries. Here a practical concept appears, the line of variation. Love. Imagine the uncertainty ellipse elongated along its major axis. You find the solutions that change the future prediction the most. IDI. Dynamicists generate orbital clones along that line and integrate them forward with all relevant forces, solar and planetary gravity, radiation pressure, and, when the case warrants, the small non-gravitational terms A1, A3 we discussed. The result is not a point in the future, but a cloud of possible positions with higher density where the model is more certain. If the data is good and the model captures the dominant physics, that cloud shrinks with each new night. A metric that interests many, even when there is no real risk, is the MOID, Minimum Orbit Intersection Distance. The minimum distance between the object's orbit and Earth's orbit. Note, MOID talks about orbits, not encounters. A small MOID does not imply impact, and a large MOID does not guarantee no close approaches in future centuries if parameters change. For interstellar visitors like 3I Atlas, the case is simpler. The orbit is hyperbolic, and the geometry generally takes them away forever. Still, calculating MOD and propagating clones serves to quantify how far it will pass and to validate that the A1 A3 terms don't drag surprises as the object crosses regions with different insulation. Dynamics centers use numerical integrations with modern planetary models. For example, ephemerides that include masses, first-order relativity, sometimes even perturbations from large asteroids. In parallel, they publish operational ephemerides that tell observatories where to point with error bars reflecting the covariance. If a key night is lost to weather, uncertainty grows. If observed right at the point of maximum leverage, where small improvements change the prediction a lot, the future cloud collapses spectacularly. This game of closing the cloud is not bureaucracy. It defines whether a non-gravitational term is real or was just a bias, decides if the rotation period we measured matters for thrust, and determines whether the narrative stays all under control or a persistent behavior appears that pushes trajectories outside the predicted. Because if after integrating clones with the best available physics the cloud doesn't shrink where it should, someone or something in the nucleus itself is moving the board. Orbital forecasting and defined physics are only as valuable as the data chain that feeds them. That's why behind every point on 3I Atlas's curve there is a journey that starts at the dome and ends in a traceable archive. In practice, night plan, sequences with precise UTC times, bias, darks, flats taken the same day, declared reference catalog, Gaia as the backbone, and a pipeline that leaves a trace of every decision. The golden rule is reproducibility, that another team with the same images can arrive at the same positions and magnitudes within the error bars. Without that, any signal risks being a mirage. Photometry is anchored with standard stars or transformations to the pan-star system when it's the closest in the field. It reports filter, aperture size, local sky method, and atmospheric extinction correction. Astrometry declares the optical model, distortion, centroid function, and the subset of Gaia stars used. It's not the same to anchor on bright stars with extreme colors as on a well-distributed mesh in color and magnitude. For comets, the coma removed dichotomy is added to clarify which position is interpreted as the nucleus. The next link is cross-quality control. Before sending to the Minor Planet Center or shared databases, many teams practice double reduction. 2 people, 2 pipelines. For example, Astrometry.net extractor versus a custom chain, and blind comparison of results. If the dispersion between them exceeds that expected by SNR, an audit is opened. Flat with gradient insufficient satellite masks, variable seeing changing the profile. Better to lose a dubious measurement than bias the entire solution. Statistics appreciate the silence of bad points. In campaigns spread over several sites, intercalibration is the hidden vitamin. Simultaneous observations or minutes-apart observations of the same field allow measuring photometric and astrometric offsets between telescopes. Those offsets are modeled, linear in magnitude, color-dependent if filters change, and applied as second-order corrections. Thus, what was a collection of islands becomes an archipelago connected by numerical bridges, ready to feed a global fit without artificial jumps. The final layer is operational publication. Ephemerides with error bars, magnitude tables with complete metadata and condition notes. That ecosystem allows external teams to attempt to refute or confirm subtle signals, like a timid A3 or a small DP, with independent data. When the community can falsify a hypothesis and it survives, the result gains muscle. And what happens when, despite everything, an outlier night appears that pushes the fit to an improbable corner of the covariance? There are 2 paths: archive the point or pursue the cause. Because sometimes an ugly datum is just that. And sometimes it's the first clue that something in 3I Atlas really changed regime while no one was looking with sufficient resolution. When an ugly datum resists audits, the protocol moves from suspicion to rapid response mode. In operational astronomy, this has a name: Target of Opportunity. TUO. A priority window that allows interrupting ongoing programs to look at a target that changed regime. It's not a whim. It's recognizing that certain clues, A jump in astrometric residuals, a leap in the light curve, a new fan in the tail are only valuable if confirmed immediately, before the comet reorganizes its activity. With 3I Atlas, the rule is clear. If an outlier survives internal quality control and independent reduction, a short list of timed verifications is activated. The first block is high-cadence optical, photometric series with small apertures and high SNR to seek newly emerged periodicities or aliases, plus coma versus coma-removed pairs to anchor the centroid. In parallel, deep imaging with aggressive satellite and gradient masking, stacked in the comet's frame, to hunt weak morphologies, new synchrones, thin ion tails. The idea: see if the change is punctual, a dated burst, or sustained. New jet regime. Rotation. The second block. If the outlier suggests additional thrust, we must ask if the fuel changed. Did CO or CO2 lines become stronger? Did CN increase without the dust continuum rising proportionally? Those comparisons, taken with the same instruments or well-crossed calibrations, transform seems to push more into it's ejecting more of X, or not enough gas. The thrust might be pure geometry. The third block is infrared. Separating reflection from emission allows estimating if the dust heated anomalously, darker or finer grains, and, therefore, if radiation pressure could have increased the bias near the nucleus. If access to mid-infrared instruments is available, better. The thermal contrast grows, and CO2 production rates are constrained with less ambiguity. There is also a millimeter radio path. When geometry and sensitivity justify it, rotational lines of COH can fix gas rates without depending on seeing and optical background. And on the space weather front, the outlier times are crossed with solar wind parameters to rule out or point out opportunistic correlations. None of this works without flexible schedules and network queues. Observatories with dynamic queue schemes can reschedule in hours. Networks of medium telescopes distribute the load geographically, and pro-amateur teams with fast cameras provide light curves that fill gaps. The common goal: collapse the covariance just when it opens the most. Because if the outlier is confirmed, the effect on the models is immediate. Clones along the LOV separate or tighten. The A1, A3 terms change sign or grow, and the brightness activity prediction veers. And at that operational crossroads, there is a decision that admits no delay. What do we measure in the next 48 hours to turn an anomaly into a diagnosis or to demonstrate that the jump was, this time, a well-made-up mirage? Designing a critical test is the heart of this effort. It's not enough to accumulate data on 3I Atlas. We must decide between competing hypotheses. The method is simple on paper and demanding in practice. Establish distinct predictions for each plausible scenario and organize observations that eliminate paths in a few nights. 3 families concentrate the serious debate. A. Thrust, dominated by classic outgassing with asymmetric jets. B. Subtle fragmentation displacing the effective center of mass. C. Residuals linked to coma and environment. Charged dust. Phase geometry we haven't fully discounted yet. For A, the vital signs are consistency between the non-gravitational terms A1, A3, and the chemistry. If COC2 grow with the predicted solar distance and AFR, dust, follows with a reasonable law, the model must reproduce the thrust direction and magnitude without asking for miracles. Decisive test. Light curves with sufficient cadence to recover a stable period, and with it predict in 1 to 9 days which phases the photometry will increase due to jet orientation. If that modulation repeats and coincides with residual changes in the expected direction, jets win. For B, the lens is morphology plus time. Finson-Probstein models should reveal narrow synchrones with a well-defined emission date. Comet-removed astrometry would still show a timid or erratic A3 if the fragments remain nearby. Extra seal, spatially coherent color changes along the tail as if new material was injected in a pulse. Falsifiable prediction. If the burst date is inferred, in subsequent nights the angular separation between nucleus and candidate fragment must grow according to the adopted velocity law. If it doesn't grow, there is no fragment. For C, the weapon is systematic comparison between centroids with and without coma in multiple filters, for example R and I, and, if possible, polarimetry. If the displacement disappears when changing filter, aperture, and applying robust masks, we're talking about coma bias, not real thrust. Additional cross, correlating residuals with solar wind parameters. A signal that breathes with the IMF affects the coma mostly, not the coma-removed nucleus. The logistical key is assigning high-leverage windows, 2-3 consecutive nights with high-cadence photometry, nucleus, a set of deep images for synchrones, and at least one synchronized spectroscopic round, all tied to a network, operational ephemerides, and complete metadata so independent teams can attempt to break the dominant hypothesis. If it survives, it's science. If it falls, the discard also advances the map. In the coming nights, the phase geometry will align such that a faint fan, if it exists, will be better contrasted, and the proposed photometric period will have its hardest exam. Predict before and be right after. If the prediction fails, one of the 3 doors will slam shut, and the story of 3A Atlas will take a turn we can no longer attribute to noise. If the method helps us discriminate hypotheses for 3A Atlas, it's worth looking at the coming ecosystem, the tools that will make these debates faster and less fragile. In the immediate future, the Vera C. Rubin Observatory, LSST, is designed to scan the southern sky with unprecedented cadence, generating millions of nightly alerts about variable and moving objects. For bodies like 3I Atlas, that means longer time arcs, earlier detections, and better sampled light curves, just what reduces aliases, closes covariances, and prevents a bad window from ruining the story. Complementing it, NEO Surveyor, a dedicated infrared observatory for near-Earth objects, promises to measure thermal emission instead of relying only on reflected light. Size and reflectance are no longer intertwined, and energy available for outgassing calculations gains rigor. That instrumental leap is supported by a silent but crucial layer: alert blockers and distributed computing. Streams like those from CTF and tomorrow LSST pass through systems that classify, cross-match, and prioritize events in real time. For an interstellar visitor, a dozen medium telescopes could receive an orchestrated list in minutes. Who does high-precision astrometry? Who takes low-resolution spectrum? Who attempts polarimetry? Who goes for deep imaging? No email chains losing hours. Dynamic queues and shared dashboards that turn a clear night into tens of useful, homogeneous points. In parallel, the pro-am culture has become a strategic muscle. Networks of 30 to 50 cm telescopes with modern cameras produce high-cadence light curves and surprisingly good astrometry when they follow standards, defined filters, consistent apertures, correct reference catalogs. In cases like 3I, where the photometric signal can be subtle, that global mesh fills gaps that no large observatory can cover alone. The key is intercalibration, common comparison stars, open reduction templates, and complete metadata. When everyone speaks the same language, small data pushes big. The last piece is organizational. IAU, PDCO, SMPIG have refined guides for targets of opportunity, time allocation rules, and criteria for scaling public communication without noise. It doesn't activate alarms by default. It creates clear routes, so if an anomaly persists, the response is technical and verifiable. In an unbound visitor like 3I Atlas, the value is not to defend anything today, but to rehearse the choreography that will matter someday. In terms of risk, all this returns to a practical question. With finer sensors, more agile queues, and a better coordinated community, what result should we already see in a case like 3I Atlas? The promise is public predictions of brightness and thrust with error bars that narrow week by week, not speeches. In the coming key nights, that promise will have its most honest exam. If the curves and centroids match what was announced, the new gear will have passed its test. If not, we must discover in which link the discrepancy we don't yet know how to name hid. Talking about 3i Atlas without noise also means talking about how we communicate uncertainty. Small body astronomy lives on probabilities and error bars, not absolute sentences, but the digital ecosystem prefers binary headlines. There, the gap between high scientific interest and silent alert opens. To close it, modern planetary defense relies on common languages that matter, the Torino scale, designed for the public, which classifies impact risk on a number from 0 to 10 with colors and time windows, and the Palermo scale, more technical, which compares the impact probability with the background noise of natural impacts in the same period. The empirical rule: the farther and smaller the object, the more provisional any rating is. This is complemented by an indispensable distinction often lost on social media: Oumuamua versus probability. MOID is pure geometry between orbits. It can be small and still no encounter because times and phases don't coincide. Probability, on the other hand, comes from orbital clones integrated in time with their real uncertainties. In a hyperbolic object like 3i Atlas, that probability relevant to Earth is, with publicly available information, negligible. That's why the community's interest concentrates on characterization, not immediate defense. So, why are there sometimes no bombastic bulletins when a coordinated campaign is mounted? Because communicating well isn't easy. We must wait for data to cross quality thresholds, for the covariance to shrink, and for results to be reproducible between teams. A premature statement can sow perceptions hard to correct. A late one undermines trust. The healthy practice in 2025 is operational publication, ephemerides with bars, live technical notes, and later, when the signal survives, understandable articles and summaries. The underlying message is not glamour, it's traceability. On the public side, there are simple antidotes to sensationalism. Distrust words like invasion, they hide, or silent, if not accompanied by verifiable data. Look for a minimum consensus among dynamic centers, telescopes, and catalogs, and distinguish between protocol rehearsal, extremely valuable, and weird alert. It also helps to look at predictions. If a hypothesis is good, it will say what should be seen when. If it fails repeatedly against honest data, it's not censorship, it's refutation. Why does all this matter for 3i Atlas? Because the real value of this case may not be an exotic revelation, but to demonstrate that the scientific machinery predicts and gets it right without shouting. If night after night the error bars keep narrowing and the light curves obey the physical script we've outlined, the story will be a silent triumph of method. But if against the script a series of solid measurements starts to disobey the model, curves falling out of phase, clean centroids insisting on impossible thrusts, the pedagogy becomes another. We must reopen hypotheses with the same calm and accept that the next watershed won't come from a statement, but from a stubborn datum that doesn't know how to keep silent. If communicating uncertainty with rigor is the what, the who and the when remain. How operational decisions are made when an object like 3i Atlas crosses the public focus. In planetary defense, there are no loose voices. There are chains of command and thresholds. The principle is simple. Evidence commands. First, dynamics centers consolidate ephemerides with closed covariances and clearly differentiated A-B scenarios. Then, technical committees, often mixed with representatives from observatories, space offices, and international coordination, evaluate if the signal survives independent reductions. If yes, a technical report is drafted describing 1. What changed? 2. How much it changed? 3. What new measurements are needed to decide between hypotheses? 4. What cannot be concluded? Only then does the public layer come in. Order matters. Why? Timing is part of the science. Announcing before consolidating a prediction can polarize the observational effort. Telescopes chase the story, not the physics, announcing later roads trust and wastes critical windows. That's why table exercises are rehearsed. Tabletop simulations, fictional scenarios with real data, where teams test if their response times, information flows, and publication criteria withstand pressure. From those rehearsals come scripts with activation points. When to issue a technical bulletin, when to request a target of opportunity, when to convene an open briefing, and under which metrics. Ethics also come in. Who speaks is not trivial. Best practice is that the speaker is the one who possesses the data and the method, with a second spokesperson explaining context and language. Torino, Palermo, Moid versus probability. That duo avoids two extremes, opaque technicism or imprecise spectacle. The living, updatable document is privileged over the single message, because in small objects every night can move the bars. Transparency doesn't mean saturation. It means traceability and consistency. This framework doesn't live in a vacuum. It intersects with civil protection, aviation, and sometimes satellite operators. Even in cases without risk, correct predictions of brightness and trajectory allow planning aerial observations, protecting sensitive equipment, and, if needed, preparing shelter-in-place protocols for atmospheric events, high-altitude explosions breaking windows, as recent episodes have documented. The social value is not only in deflecting, almost never possible short-term, but in predicting and preparing. And what does that teach us in the context of 3i Atlas? That even when the probability of damage is negligible, exercising the discipline of thresholds, spokespersons, and simulations pays off. It turns data into decisions and narratives into trust. But there is an uncomfortable question this choreography doesn't solve by itself. What happens when the sky doesn't give enough warning, and the first real alert is an intense light on the horizon and a pressure wave seconds later? The usefulness of this entire system is ultimately measured on that kind of morning. When the first alert is a flash in the sky and a pressure wave that makes windows vibrate, we are no longer talking about hypotheses, but about atmospheric entry physics. Documented cases teach a simple and compelling lesson. For fragments of tens of meters, the typical danger doesn't come from a crater, but from the airburst, an energy release at altitudes between 20 and 40 km that generates a shock wave capable of breaking glass over wide urban areas. Scale matters. A Chelyabinsk-sized object, 20 meter, releases energy comparable to several tens of kilotons if it arrives fast and at an unfavorable angle. But material also matters. Porous bodies disintegrate high, more compact ones penetrate deeper. The practical result is a range of scenarios where rupture altitude, angle, and velocity decide how much damage reaches the ground. What can be done before and during if the warning is short? Before. Basic education and clear protocols. Don't look at the flash against the light, move away from windows, place people indoors, preferably in corridors or stairs where glass is less prominent. During, simple rules that save fingers and eyes. Wait a few seconds after the flash because the thunder arrives late. All this is Civil Protection 101, not science fiction, and can be communicated with the same sobriety with which we talk about ephemerides and covariances. And what does this have to do with 3i Atlas if its risk is negligible? A lot, because every rigorous campaign fine-tunes three things that do count on difficult mornings. 1. The speed with which we go from detection to useful prediction, even if only of brightness and trajectory. 2. The quality of public communication, putting in writing what is known, what is not, and what behaviors to adopt. 3. The trust between observatories, agencies, and civil protection to activate brief, actionable messages without frills. Rehearsing with an interstellar visitor educates the system for the day. An inbound intruder of modest size changes our agenda in minutes. A fine point here is the relationship between uncertainty and decision. Waiting for absolute certainty is sometimes losing the window to prevent simple damages. Restricting traffic on bridges, warning schools to keep children away from windows. That's why operational thresholds are not when we know everything, but when we know enough and the cost of saying nothing is greater. That philosophy, applied with criteria, avoids both paralysis and overreaction. With 3i Atlas, the merit won't be activating sirens, not applicable, but demonstrating that a scientific ecosystem can translate data into clear guidelines without distorting the risks. If that muscle responds well when the case is calm, there will be real reason to trust when the sky asks for quick moves, and there is an arena where that translation becomes a delicate art: the classroom and the public square, where a well-explained graph can be worth more than 1,000 headlines. If we talk about translating science into clear guidelines, the next terrain is education and public culture. How do we tell the story of 3i Atlas so that people remember what truly matters? A documentary like this helps, but the fine work happens in classrooms, museums, and local media. There, it's good to change the focus. Less mystery and more tools. 3 didactic pieces make a big difference. The first is a simple sky map with public ephemerides and error bars, teaching that prediction is not a perfect point, but a cloud that closes with data. The second is a timeline showing what we measure: position, brightness, spectrum, when and why that changes the model. Thus, the public understands the process, not just the result. The third is a word traffic light, recommended words: probability, uncertainty, observational window, and words to avoid: invasion, secret, panic, with examples of good and bad headlines. On social media, pedagogy becomes micro, clips comparing the before and after of an orbit after adding 3 good nights, 30-second clips showing how the coma can bias the centroid and why decommeting astrometry is crucial, infographics explaining the difference between MOID, orbit geometry, and probability, integrated scenarios. If we add minimal metadata, filter, aperture, reference catalog to each graph, we habituate the audience to demand quality, not just pretty colors. There is also a huge opportunity in well-guided citizen science. Small telescopes can contribute high-cadence light curves if they follow a protocol. Use the same filter per night. Maintain consistent photometric apertures. Report the local sky and anchor magnitudes to adequate catalogs. Open platforms allow intercalibrating contributions and quickly distinguishing who measured within the norm and who didn't. The key is feedback. A timely technical comment avoids repeating errors and turns volunteers into collaborators. In the media, the best cure against noise is coherence. Spokespersons who speak the same way on TV, radio, and press, living documents with dated updates, and an editorial rule that privileges falsifiable predictions over adjectives. If we say that on such date the curve will rise due to jet orientation, or that the uncertainty ellipse will halve with X observatory, the public can verify. Being right reinforces trust. Failing and correcting, if well explained, also reinforces it. All this, classroom, social media, volunteering, and press, weaves a social habit, looking at the sky with criteria. And right now, that criteria is about to be tested with 3i Atlas. The coming windows promise data that, if the method is solid, will nail the direction and size of the non-gravitational thrust, or exhibit a stubborn discrepancy that will force us to reassemble the puzzle out loud in front of everyone. If we remove the operational curtain, 3i Atlas puts us before the big question: what does an interstellar visitor tell us about where and how worlds form? With 3 cases on the table, Oumuamua, Borisov, and now 3i, it's not enough to dictate laws, but to map possibilities. The key: compare chemistries and dust properties with what we see in local comets and in protoplanetary disks around other stars. In disk spectra, we have identified ices of H2O, CO, and CO2, plus simple organics. When an interstellar object shows different proportions, we shouldn't jump to the exotic. It might be saying that its stellar cradle was colder, fainter, or that its thermal history was different. with irradiation cycles that tanned its surface unevenly. In that sense, 3I Atlas is valuable even if it doesn't break molds. If its CO-CO2 lines appear early at a greater solar distance and water dominates later, it would reinforce the pattern that colder volatiles govern the start of activity in objects formed far from their parent stars. If instead its spectrum looks terrestrial, predominant water, Cn and C2 in known ranges, it wouldn't be a disappointment. It would consolidate the idea that the basic chemistry of the galactic neighborhood repeats and that big differences come more from structure and history, porosity, cracks, crusts, than from strange molecular recipes. Dust tells another part. Disks observed with ALMA reveal size gradients and rings where grains grow or migrate. If 3I Atlas shows a size distribution skewed towards fine grains, high K, or coarse grains, low K, that bias could be a fossil of its region of origin. Polarimetry refines even more. Porous, fluffy grains polarize differently than compact grains. If the pattern matches what we infer in disks, 3I could be our hand sample of processes we only see from a distance. This comparison also serves to deflate ghosts. If a non-gravitational thrust seems large in 3I, but the inventory of volatiles and the dust rate are enough to explain it, the extraordinary becomes plausible. Well-oriented jets, not technology or new physics. If not enough, the next step is not speculation, but geometry. Spin states, thermal lags, valving. Even so, every adjustment that fits reduces the margin for fanciful readings and feeds population models. What would the census of visitors be like if our surveys were ideal? And there selection bias appears. We detect better what is bright, slow, and well-placed. Smaller, faster visitors, or those with timid activity, pass by unnoticed. 3I Atlas, measured with rigor, helps us calibrate how many we miss and why, because understanding its chemistry in dust is only half the picture. The other half is accepting that the universe is sending us pieces we don't see yet. If we want to tell their complete story, we will have to adjust not only models, but the way we look. If 3I Atlas helps us measure better, it also puts the logistical question on the table. Can we go see an interstellar visitor up close? Today, the honest answer is, only if it gives us enough notice and if we have something ready to go. The difficulty is not romantic, it's orbital dynamics. These objects arrive with high relative velocities, large dV, and non-repeating trajectories. Any rendezvous attempt requires tight launch windows, high dV, or strategies to wait in an advantageous spot and launch when a candidate appears. Hence the operational idea of an interceptor on standby. The philosophy is simple. Instead of designing a mission after discovery, when it's too late, a probe is launched into a parking orbit, for example, near L2, with fuel and maneuver profiles ready. When a target is detected with sufficient lead time, the probe executes a fast flyby with cameras, spectrometers, and, if possible, polychromators and LiDAR for morphology and dust. This architecture doesn't promise postcard images. It promises opportunistic data: composition, size, rotation, activity, grain. The scientific cost of only achieving a flyby is widely paid by being the first in situ glimpse of another star. Why don't we do it already for all? Because engineering imposes trade-offs: useful mass versus dV, range versus available solar energy, dust shielding versus weight. And above all, because detection statistics don't yet guarantee that a standby probe will definitely find a target in its lifetime, if the alert comes late or with impossible geometries. Precisely why 3I Atlas and the upcoming surveys we mentioned matter so much. Earlier detections, better determined orbits, and reliable light curves open weeks or months of margin that don't always exist today. And 3I Atlas in particular, with publicly available information and typical preparation times, the reasonable thing is to see it as a general rehearsal for this type of architecture. Not as a real interception candidate, but even so, it helps define the minimum viable remote science that a future mission should complement. Which spectral lines are most worth measuring up close? What phase resolution and which infrared band best separate dust and gas? What cadences allow us to hunt in situ with ground-based telescopes? The other half of the equation is decisional. What would be the threshold of anticipation, brightness, geometry that would activate a mission alert without falling into impossible bets? It's rarely said aloud, but it's the point where science, engineering, and cost look each other in the eye. And in the kind of weeks 3i Atlas gifts us now, that conversation stops being theoretical. It becomes a calendar with underlined days, each with its price in DV and its promise of finally being the first human approach to a visitor from another star. If thinking about interceptors leads us to engineering, there is a foundation that supports everything else: open and irreproducible data. In ephemeral objects like 3i Atlas, the difference between trust and speculation often boils down to whether anyone can recalculate what we claim. The modern ecosystem already has pieces, but forces us to use them well. The Minor Planet Center centralizes astrometry and publishes MPX circulars with ephemerides and weights. Archives like Pan-STARRS, CTF, and professional consortia upload raw and calibrated images. Analyses appear on ArXov, later in peer-reviewed journals. The bridge sometimes missing is complete traceability. Not just the final number, but the how I got there. For a case like 3i, reproducibility means 4 things. First, that every point of position and brightness is linked to metadata: filter, photometric aperture, reference catalog, U-Gaia, distortion model, SNR, sky conditions. Second, that the pipelines, code from centering to photometry, are available even in a frozen version, Dewey Comet, so another person can execute the same recipe on the same images. Third, that the decisions, which points were excluded, why, are recorded. A table of rejections with reasons avoids suspicions and allows useful audits. Fourth, that predictions are published with bars and a cutoff date. With data up to night X, we expect Y + Z. Thus, the public and external teams can verify a posteriori if the model was correct or needs correction. There are practical limits. Not all observatories can open all their data immediately. There are PI rights, schedules, and storage costs. Still, there are hybrid forms that work, opening critical subsets, for example, the nights that most collapse the covariance, releasing centroid and photometry catalogs with their errors, and sharing scripts that allow recomputing decommitted positions. In photometry, reduction templates and comparison star lists level PROAM networks so they contribute without introducing invisible biases. The other gain from this culture is pedagogical. When a falsifiable prediction is published, for example, if the jet orientation is correct, the photometric period will show a maximum around such date and the residuals will drop in such direction. The next bulletin is no longer rhetoric. It's a verdict. Sustained successes reinforce the sober narrative. Well-explained errors strengthen trust. The method corrects itself in public. Atlas, by itself might not change solar system history, but it can move the needle on how we tell what we do. With open notebooks, dated versions, and a language that prefers "this we know, this we don't" to adjectives. And right now, on the verge of a key observation window, a data package promising to release. Centroids and light curves with complete metadata could decide whether the non-gravitational thrust we hint at is robust or if a well-documented correction once again rewrites the script, with the peace of mind that comes from being able to recalculate everything. When data volume grows and hypotheses compete, the best compass is not the model's charisma, but well-done Bayesian inference. For 3i Atlas, this means framing the 3 families we've outlined. G, pure gravity, NG, gravity plus non-gravitational terms A1, A3, if, scenarios with fragmentation, incidents, within a scheme that compares explanations by their evidence and predictive power. In practice, we define likelihoods, how probable it is to observe our positions photometry given a set of parameters. Choose realistic priors, for example, amplitudes of A1, A3 compatible with measured gas production or physical distributions for burst dates if we consider F. And let the data update beliefs. 3 tools rule. The first are posterior predictive checks. You generate replicas of the time series, positions, decommitted centroids, magnitudes, from the posterior distribution of each model and compare with the observed. Model NG reproduces not only the mean, but the dispersion and temporal structure of the residuals better than G. It gained a point. If F manages to nail breaks in dates that also coincide with synchrones and color changes, it adds another. The second is penalization for complexity. Adding parameters almost always improves the apparent fit, but criteria like wake or low OCV, leave one out cross-validation, penalize overcapacity. If NG or F don't sustain the improvement out of sample, they fall by their own weight. The third is sensitivity to priors. You reevaluate with wider, narrower priors to verify the conclusion isn't an artifact of a hidden assumption. In parallel, astrometry demands honest error models. Symmetrical Gaussian assumptions aren't enough. Nights with variable seeing, residual trails, or limit conditions can inflate tails. Modeling errors with heavy tails, e.g., student T, avoids a few points artificially straining the parameters and, paradoxically, protects real signals by not blowing up the fit with outliers that don't deserve so much weight. On the photometric side, incorporating correlated noise, for example, smooth trends due to lunar background, prevents inference from seeing periodicities where there's only instrumental drift. The magic and duty lie in the forecast. With the posterior in hand, each model must publish falsifiable predictions, expected direction and magnitude of residuals in the coming nights, phase, maxima, minima in the light curve if spin modulates jets, and even how AFR should change if a burst was real. That agenda turns statistics into a calendar. If G wins, we will have purged biases until we are left with clean gravity and a lesson in method. If NG prevails, 3i Atlas joins the catalog calibrating outgassing thrusts in interstellar visitors. If F resists, we will have a fragmentation clock to count. The decisive thing is that in the hours that follow, a batch of high-quality measurements will put these 3 prediction curves to compete in public. And when one of them fails spectacularly or succeeds with uncomfortable precision, the narrative will stop being a promise and become a diagnosis. The decisive phase of 3i Atlas is not measured in adjectives, but in operational verdicts. Did our public predictions hit within their bars? Did the covariance cloud contract as promised? Did the non-gravitational terms, if adopted, remain stable when incorporating new nights? These answers, more than closing a story, calibrate a system. Because the heart of the matter, what some called the biggest silent alert, is not a siren but a culture of verifiable vigilance. Refined since 1997 when a misunderstanding with XF11 taught that communicating uncertainty without method invites noise. Today, the exam is more sober. Demonstrate that the machinery can predict, publish, and correct without drama. There are 4 metrics of success that do matter. The first is fulfilled prediction. Light curves reaching maxima, minima in phase, astrometric residuals following the announced direction, AFR scaling as anticipated with solar distance. The second is robustness, that the fit doesn't depend on a single bright night or a single telescope, but on a coalition of intercalibrated data that survives cuts, leave one out, and alternate pipelines. The third is traceability, that anyone can retrace the path, images, metadata, frozen code, and arrive within reasonable errors at the same verdict. The fourth is cycle time. How long did it take us to translate a clue into a 2.0? Coordinate spectra, choose deep images, publish updated ephemerides. If that cycle shortens without losing quality, the silent alert stops being a slogan and becomes capability. No less important is what we discard. If the fragmentation hypothesis doesn't survive synchrones and color, if the impossible evaporates upon decommeting with crossed filters, if the solar wind doesn't correlate with clean residuals. Those negatives are not defeat. They are victories of method that free attention for the physics that remain standing: jets, thermal lag, spin. Every closed door reduces the temptation for fabulations and amplifies trust in the sober reading of an interstellar visitor. There remains, however, a deeper level. What changes in us after 3I Atlas? If everything behaves as expected, we will have consolidated a choreography that tomorrow will serve for bound and less indulgent objects. If a stubborn discrepancy appears, the response is not panic, but learning in public. Opening data, adjusting priors, inviting replicas. In both cases, the measurable balance is the quality of the social contract between science and society. We believe in systems that show their work and accept corrections in plain sight. Because in the end, that's what was being tested here. Not whether there is a secret or something is coming, but whether we know how to look and tell without deforming. And just when the last batches of observations enter the board and the 3 model families publish their final forecasts, one figure begins to stand out above the rest. It's not a headline. It's a simple number that decides whether this story is filed as impeccable routine or opens a new line in the notebook where we write what we don't yet fully understand. A good documentary ends where it begins, with a clear question and an honest answer. Was 3I Atlas the biggest silent alert since 1997, or the best proof that since then we learned to watch without shouting? If you're still here, you've seen the difference. What some sell as secret is actually discipline, coordinated observation chains, decommitted astrometry, spectra separating dust from gas, light curves revealing spin, and models publishing falsifiable predictions. From the media stumble of XF-11 in 1997, Planetary Defense has become less heroic and more methodical. And 3I Atlas, with its rarity as a visitor from another star, held up the mirror to us, not of alarms, but of operational capacity. So, what does this journey leave us with? First, a compass, gravity, data, and humility. Gravity to not get lost in unsupported hypotheses, data to close covariances with robust series, humility to accept that with 3 interstellar visitors in the record, the plural of anecdote is not evidence. Second, a toolbox that should no longer be stored away. Finson Probstein to read the dust calendar. A1, A3 terms to quantify tiny thrusts, polarimetry and infrared to inventory volatiles. Bayesian inference to decide between models without falling in love with any. Third, a way of speaking. Torino and Palermo for risk. MoID versus probability to not confuse geometry with destiny. Living documents and reproducible data so anyone can recalculate. It also leaves us a map of the immediate future. With Rubin, YEL-SST, Neo-Surveyor, and alert blockers, early detection will become the norm, not a lucky break. That flow demands something 3I Atlas already probed. Intercalibrated pro-am networks, dynamic cues for TUO, and a culture of publishing before opining. And if someday a visitor arrives with generous launch windows, what was learned here will be the foundation of an interceptor on standby. Less poster and more in situ science on time. But the most important balance happens outside the dome and console. It happens in the public square. This case showed that uncertainty can be told without turning it into myth. That a "we don't know yet" gains respect when accompanied by what needs measuring and when we'll know more. And that the antidote to the inflated headline is not silence, but traceability. Ephemerides with bars, complete metadata, and the courage to correct in public when a stubborn datum forces you to move the model. Was it then the biggest silent alert? If by alert we mean sirens, no. If by alert we mean a general rehearsal of everything that must work when someday it does matter, then yes. 3I Atlas was a wake-up call answered with numbers, not nerves. And that, in a world that confuses volume with truth, is a victory. When you close this video, the Comet will continue its hyperbolic route towards nowhere we can visit soon. But what it does leave us is a tangible measure of our maturity. The capacity to predict, publish, and learn without frills. Let that be the standard from today. Because the sky doesn't negotiate deadlines, and the next time a visitor knocks on the door, the only alert that will matter will be that of a system that knows how to look well and act in time.